In previous lecture, I have discussed the sum property of Laplace transform. And in this lecture, I will also discuss two more property of Laplace transform. One is what will happen when you will multiply any function ft with t, and other thing is what will happen when you will divide any function with t, how the Laplace transform of ft will change after multiplication or division with t. So this is the first statement. If Laplace transform of any function ft is known, it is available which is equal to fs, then by using this property you can easily determine the Laplace transform of tft. And the Laplace transform of tft will be equal to differentiation of fs with respect to s with negative sign. So if you have an idea of Laplace transform of fs ft which is equal to fs, then by differentiating this fs with respect to s, you can get the Laplace transform of tft. So how you can prove this statement? As you know, the Laplace transform of any function ft, which is fs basically, which is fs, and will be equal to the integration 0 to infinity ft to the power minus st dt. This expression already I have discussed in the previous video. Now you will have to differentiate this expression with respect to s. When you will differentiate this expression with respect to s, then what will happen? This t, because the coefficient of s is t here, so this minus t will exist in the coefficient of ft. So when you will differentiate fs with respect to t, you will get this expression minus t ft e to the power minus st dt. And obviously here in place of ft, there is tft. So this is Laplace transform of tft basically. So this is the Laplace transform of tft, and this minus sign can be shifted here. So Laplace transform of tft will be equal to minus of dfs by ds. In this way, you can prove this statement. And by using this property, you can derive various other Laplace transform of various other function also. For example, what will be the Laplace transform of t into sine omega t? So here you can see sine omega t is multiplied with t. So its Laplace transform will be minus dfs by ds. Here fs is the Laplace transform of ft, and the role of ft will be played by sine omega t. Here ft is sine omega t, and the Laplace transform of sine omega t is given by the expression fs equal to omega by s square plus omega square. So just you have to differentiate this expression with respect to s, and you can get the value of dfs by ds, and you will have to keep minus sign also here. So in this way you can get the Laplace transform of t into sine omega t. So this property is very useful to find out the Laplace transform of various other function which is multiply with t. Similarly, the other property is division of t. What will happen when you will divide any function ft with t? How the Laplace transform will change? If you have an idea of Laplace transform of any function ft which is equal to fs or function of s, and you have idea of that expression, then you can easily get the Laplace transform of ft by t. And this will be equal to, according to this property, it will be equal to integration from s to infinity fs ds. So how you can justify, how you can prove this statement? As you know, the Laplace transform of any function ft is written with fs because the Laplace transform convert time domain signal in frequency domain signal. So Laplace transform of any function ft will be equal to fs, which is given by the integration 0 to infinity ft to the power minus st dt. Now take right hand side expression. The right hand side expression is s to infinity fs ds. And you will have to prove this expression will be equal to Laplace transform of ft by t. So in place of fs, you can substitute this value. In place of fs, you will have to write the expression of fs here. So fs is integration 0 to infinity ft to the power minus st dt. So this is fs. This is fs. This is fs. And this ds is here. So you can write this integration with this term. Now you can readjust the term. Readjust the term means you can keep ft here and ds here. You will get this expression. And when you will integrate e to the power minus st ds from s to infinity, obviously you are going to integrate this expression with respect to s. So coefficient of s is here t. This t will be in denominator with minus sign. So you will get this expression from s to infinity. And this ft is here. And this dt is here. And when you will substitute, this is upper limit and this will is the lower limit. And you will have to substitute upper and lower limit in this expression. And when you will put t equal to s equal to minus infinity, then you will get 0. And when you will put s equal to s, you must remember here, this is integration with respect to s. So here you will have to put s and infinity in place of s. You must remember here. So when you will put s equal to infinity in plus, then you will get 0. And minus, when you will put s in place of s, then you will get e to the power minus st by minus t. And minus sign will become plus. So you will get finally this expression. Once again, I am substituting the limit. When you will substitute, this is ft. And when you will substitute e to the power minus infinity, then you will get 0 minus. When you will put s equal to s, then you will get e to the power minus st divided by this minus t. And then this is dt. This is dt, and this integration is 0 to infinity. So in this way, you will get this expression. And obviously here you can see in place of ft, here is ft plus t. So this is the Laplace transform of ft plus t. This is basically a Laplace transform of, this is Laplace transform of ft by t. So in this way you can see integration s to infinity fs ds is basically a Laplace transform of ft divided by t. So these two properties are very important to determine Laplace transform of function, which is multiply or divide by 2. In next video, I will discuss some numerical example based on this property.